Awesome. Looks like a couple people are still trickling in, so I say we should probably start at like 5:10 if that's cool with you.
All right.
Hey, Mark, in case you didn't see it, there's a question for you in the Q&A.
All right. Thank you. Yeah, I wasn't paying attention. Yeah.
That's okay. I don't think it's too serious of a question.
Yeah, it's Stephen Big X. Hi, Mark. Thanks for all your support. How did the big storm turn out for you?
I was lucky. I'm actually not in Dallas. I'm in North Carolina. But yeah, it was a huge weather event. Of course, we had a lot of disruptions at work because everyone's working from home. So you got to navigate all that on your own personal level. But yeah, I think everything's starting to get back to normal now. But obviously, it was very stressful for a lot of people.
Yeah, for sure. Yeah, I have family in Texas, so I'll probably have to check in with them, see how they're doing.
You should. Okay, let me get my slides up here. So what's the format this year? Is it still one weekend, or is everyone starting to work now? Or
Yeah, so everybody's gonna fire it up on Friday night, I believe around like 4 p.m., 6 p.m. is when we'll have kickoff, and then that'll go all the way until judging on Sunday. It's gonna be super fun. I'm competing this year too, so I'm excited to see what you talk about for IoT. I actually just got the LPSTK for one of my classes, so I'm excited to try to use it.
Yeah. I'll touch on that a little bit today.
Awesome.
All right, should I just go for it now?
Yeah, go for it. Take it away.
Hey everybody, thanks for joining the TI Lightning Talk here. We're going to be covering the kind of just IoT aspects of it. Obviously with a hackathon, it's like very hard to pick a certain thing that it's going to be relevant to everybody. But I figure if you all are doing any kind of embedded system stuff or anything with a processor, microcontroller, hopefully this is like somewhat relevant to what you guys will be doing over in MakeOHI. So let's see, do I have an intro slide for me in here? No, I don't. Okay, well, I'm Mark Easley, everybody. And yeah, I'm with TI's university program. I'm helping support our sponsorship for the event. And yeah, I've been at TI coming up almost 9 years now. Graduated from Notre Dame and then went straight to Dallas, worked for TI, and my background's in embedded system and IoT. So if you guys have any questions, please feel free to ask in the chat or let me know after the talk. Happy to help out with any questions you might have. So just a rough overview of the semiconductor industry, which TI is in. Oh, excuse me. This is a really great field of work potentially for all you electrical computer engineers out there. And just to give you an overview, the semiconductor industry, we're the chip makers. Our semiconductor material of choice is still silicon. This is the tried and true material for all our devices. There are some new ones coming out, things like silicon carbide, gallium nitride, but the majority of devices are still pure silicon. Now you could derive that silicon, of course, from sand if you wanted to, but how we do it is actually artificially create it. When we do that process, it forms these big cylinders that you can see in that second column. And in those cylinders, we actually slice into these super thin discs, and those are the silicon wafers. So those wafers are our medium or our canvas that we use to create the devices. Then on that third column, you can see in there, that's what we call the die, the individual insides of the chip, the guts of the chip, if you will. And basically, even though the wafer itself is kind of like a 2D plane, in the process of making the devices, we actually build it in a kind of a 3D manner. So within that silicon, there's layers of the circuitry going through there, and that's creating a device itself. And then we actually cut out those little squares, and that's our individual chips. And then we package them up into our final product, which is the actual, devices, the black plastic packaging that you see on your printed circuit board and stuff like that. And that's the products that TI sells and other companies in the semiconductor industry work on. So obviously that's a very high level explanation, super high technology, tens of thousands of people making this work every single day, billions and billions of chips being manufactured every year. But it is a very exciting, cool field. So these chips, they go into obviously all kinds of cool end equipment. You can think of pretty much anything that's got power to it, right? It has some electronics, has a circuit board inside. And that's what a lot of TI supports, all kinds of analog and embedded systems type products going into test equipment, medical equipment, wireless infrastructure, personal electronics, personal transportation vehicles, all kinds of different things you can think of. And all we're doing here is, of course, signal chain manipulation. So a lot of these integrated circuits, they're focused on, taking real world stuff, like maybe you got speed, temperature, these kind of things, analog signals, waveforms. We need to amplify those signals. We need to filter those signals. We need to get them into a digital context so we can implement logic and programming onto them. And then we need to kick it back out in the analog world again, maybe to drive some motors, flip some LEDs on and off, those kind of things. So anytime we're building any kind of electronics, we're always doing the signal chain type stuff. And that's what a lot of these integrated circuits are helping with for our individual applications. So TI, we've been around for a long time. We're actually 90 years old. Started in 1930, trying to help people out in Texas find the oil out there was our initial start. But a lot of cool innovations along the way, but the biggest one, of course, was 1958. We had an engineer at TI named Jack Kilby, and Jack is accredited with the invention of the integrated circuit. So basically, he's the kind of the start off the whole thing around semiconductors, and ever since then, TI has been in the semiconductor industry. And a lot of engineers have been working all kinds of cool stuff, processors, microcontrollers, amplifier, all kind of great analog circuitry. And that continues for decades, to this day, where we need those things more than ever before. So if you guys are interested, we are still hiring, I think, a few things. A little bit late in the season, but if you want to check on careers.ti.com, we still got some of our internship postings as well as full-time if anyone's graduating. Again, if you have any questions, feel free to let me know. But obviously, this talk is more for the design part of things. So when we're talking about the design, I know it's a little bit complicated this year because we've got all the precautions around the pandemic and things like that. So I kind of generically just set up this slide so you can see some of the things you should be thinking about if the whole team is maybe not in the same place or things like that. You just want to make sure you're scoping your project appropriately so that you're accommodating for either the distributed team or not being able to be face-to-face with, things like mentors or help or whatever. Just be cognizant those are some difficulties that we'll have to navigate in this kind of environment. Always be prepared as well for team members. They just got to be flexible, know what everyone's working on, so that you're constantly communicating and know how things are progressing. Obviously, over the course of a weekend, it's a very compressed time frame, so may not be as big of a factor. But this is more for in general when working on any kind of design stuff. Use of software, make sure you either have a cloud version of it or a local version you can install, so you can always be working on stuff, whether you're in person or remote. And then the hardware portions, you want to utilize a lot of the prototyping solutions that exist. Luckily, now more than ever, there's so many great and convenient solutions that we have. You can go out to, shops like Adafruit and SparkFun and get these prototyping boards, and go to DigiKey and get stuff shipped in real quick, or Mauser Electronics, or you can go to some of the individual manufacturers' websites if you need certain sensors or something like that. And they usually have breakout boards for the devices. So it's easier than ever to kind of get started with the design. And with a hackathon, of course, you're just trying to build a proof of concept or basic demo or something like that. So make sure you're taking advantage of those kind of things. Don't get overly concerned with the what kind of more intensive design aspects that you would probably have to do for a real product or something like that, but definitely take advantage of those prototyping solutions. Things like development boards, pre-made modules. Again, these are all things you can get shipped to your location very, very readily. This is probably not so relevant for you all with the competition, but if you did want to make a printed circuit board, that's also very doable. You can basically design your PCB, send that off to a manufacturer, get it back in a couple days. So it's difficult, but not impossible. It's actually a very normal way to do that PCB stuff is remote. So not a huge deal there. Another consideration, of course, you won't have access to as much equipment necessarily. So things like soldering, things like test and debug with good equipment, that may not be accessible. So just be aware of that and make adjustments. Using things like GitHub and other tools for collaboration and sharing between team members, also very, very crucial. So everyone's on the same page. And yeah, those are some important considerations. So whether we're building our single idea for MakeOHI or we're building 1 million Apple Watches, the process is always the same, right? We probably have some kind of problem we're looking to solve, or some kind of new technology solution that we think would fit to help out in an application. So basically you're conceptualizing what those are, right? You're researching what technologies are available on the market today that could address those, or future cutting edge technologies that might be applied to that. You're evaluating those solutions. So like I said, you're going out and getting development boards, you're getting breakout modules and evaluation modules and stuff like that. You're putting those together, try to get them to work. You're trying to 3D print some concepts around things that you might need. You're iterating on that constantly, figuring out how you can actually get that first proof of concept through, and then and prototyping all that. Then you're also figuring out how you're going to fund this thing. So if it's a larger company, you're out trying to get some budget. If you're in a startup company, you're going out and trying to find some investors. If you're in academia, you're going out and trying to find some grants, et cetera. Another step is marketing. So who's the customer? Who's the user of this solution? How do they want to use the product or service? How do they want to pay for it as well? What's the business model around it? The pricing, usability, et cetera. Those are all super important questions. As engineers, we're constantly working with marketing people, business people to figure out how do we make our design sustainable, so that people can use it and use it for the long term. And then production, this is also a big one, obviously not as important for you all for the hackathon, but there's a whole bunch of philosophies around how you do design, and basically design for scale. So manufacturing at scale. There's a big one called design for manufacturing. Lots of material online you can find about it, but essentially there's certain ways you can design a prototype or even a product that will take advantage of things like economies of scale, basically lower the cost, but also have plenty of supply chain available so that you can build those products at scale. So yeah, lots of philosophy around all that. And that's a whole kind of science and art to itself. And then you've got your distribution. How are people going to get access to your thing you designed? Is it direct to consumer? Is it something you put on Amazon or Walmart? Those kind of things. And then how you support that product once it's out in the wild. So that's kind of the very common path that everyone takes for any kind of design project. Now for Internet of Things specifically, and this is basically, like I said, if you're doing any kind of project with a processor or something like that, there might be certain Internet of Things aspects to it that you'll want to integrate. So something like a wireless connectivity or sensing or stuff like that. So here's a couple use cases for IoT. One being, of course, asset tracking. So there's a lot of things we want to monitor, right? Something's going from A to B. We want to monitor some trucks in a parking lot, something like that, right? So creating that ability to give people insight into that kind of data, location data, asset tracking data, those are super important parts of the Internet of Things. Another big one being preventative maintenance. So we're talking about like a factory situation where you have a lot of expensive capital equipment. You obviously want to make sure that stuff doesn't break down. So if there's ways that you can monitor that equipment for different failures or it runs out of certain things, you can schedule your technicians to take a look at that and keep the factory rolling, at maximum capacity, et cetera. Automatic replenishment. So anytime you have something that's a consumable, so think of like maybe like a hand sanitizer dispenser or a paper towel dispenser, right? That thing will eventually run out, and then you have to send someone to refill it, things like that. So it's that kind of data where you can keep, again, efficiencies on things that you have to replenish. Very, very important. Environmental monitoring, this is a big one. So things, all kinds of just things around temperature, humidity, you know, if things get too hot, they get ruined. If things get too cold, they get ruined, you know, so figuring out all that kind of stuff. Data information access, so ways that we as humans or users can get data. So that could be something like a smart speaker, it could be something like an interactive screen, fitness tracker, watch, those kind of type of applications, getting data that's important to us as users. And then compliance reporting, this is things like healthcare stuff, maybe insurance stuff, like looking at things like, are you a good driver? Something like that, right? So all kinds of cool IoT applications. Now for your basic IoT product development, there's kind of these very high level things you should be doing. One, of course, is creating a block diagram. And this is important for any embedded design, but with IoT, you want to be very clear on what are the components. So have a block for, you know, each thing. Is it a sensor? Is it the processor? And then very specifically, what is it inside of those? And then you're going to have, of course, lines going to all your different blocks. And between those lines, what are the connections? Is it power? You know, what voltage level power do you need for these different things? If it's communications, you know, what kind of wireless or what kind of protocol are you using to connect the blocks, et cetera. So you want to be very clear of how the system is laid out, and that will really help you build the design much more effectively. And then again, prototyping with the different ready-made prototyping tools, like the different evaluation kits and development modules, things like that. Then you're going to design your PCB. So again, this is not so relevant to you all, but you know, if you were making a IoT product, you'd want to make a custom design with a printed circuit board fit to your application, because you probably have something like size requirements or power requirements, et cetera. And that's going to involve, you know, a custom printed circuit board. And then you're going to write on your software, your firmware, that's going to run locally on the processor. And then you're also probably going to develop some cloud capability. So you might be connecting to some kind of cloud service, or you need to hook up into a network, something like that. So figuring out all those different APIs you might need to interface with, or network access that you need to interface with. So for TI, we've got a couple different options as far as like ready-made things. So one is the Launchpads. These are microcontroller boards. And again, if you need some kind of microcontroller, plenty of options that we have at TI. This one's a pretty popular one, MSP432. This is an ARM-based Cortex M4, good just general purpose microcontroller. And then these Launchpads are nice because they do have the onboard hardware debugger, and they have the, just like any kind of development board, the prototyping pins. So you can either plug in pre-made modules, you can interface these microcontrollers to a breadboard circuit, et cetera. Another one that's interesting for IoT is this one, which is the Launchpad Sensor Tag. We call it LPSTK, but Sensor Tag for short, I guess. And this is kind of a ready-made microcontroller IoT design. So it's got an onboard radio integrated with Bluetooth and longer range, kind of sub-gigahertz RF. And then it's got, again, really nice specs for ARM-based device. And you can basically have a ready-made IoT sensor here with a couple of different sensors out of the box. So that's a nice one for prototype if you're doing just like a sensor network or something. It's pretty easy to get started with that. It's inside the sensor tag. Okay. So in sensor IoT specifically, if you're doing something where you need to deploy these sensors in a wide variety of ways, they have typical characteristics. So a big one, of course, being long range. You know, in a factory floor, for example, again, we might have a central gateway, and then we have a bunch of sensors deployed throughout the factory, right? Maybe it's monitoring equipment, maybe it's monitoring factory usage of people, you know, moving around or something like that. So again, all those are deployed in kind of a similar area, but they need to talk, you know, long range. And then density, either, for example, a smart city or in the factory again, you know, you have a lot of these sensors all talking together. How do you coordinate all that high density traffic, RF traffic? Low power capability. So obviously we don't want to run, you know, line power to some of these sensors. We want to just deploy them, you know, anywhere. So that means battery power. So we got to make sure these sensors are low power. And then also these sensors are usually pretty simple. So they're sending maybe some basic temperature data or some other kind of small data packets. So they're relatively low bandwidth. You don't need a ton of capability on the data pass. A lot of these sensors will use what we call I2C protocol. So this is just good in general. If you want to interface any kind of sensors, it's good to understand what this I2C protocol is all about, how to implement that in the embedded context for whatever processor you're using. Because like I said, a lot of these sensors will have this I2C interface that you can basically hook up a whole bunch of different types of sensors together. And then you have all different kind of RF protocols. Some customers like to have a proprietary RF. This is so they can have the lowest latency possible. But there's a lot of people that like to just use standard stacks. So there's all kinds you may have heard of, like Zigbee, XB, etc., Thread. These are all stacks you can utilize, and they all have documentation about how to use them and everything like that. And you just select the appropriate radio that will run for those stacks. So TI, we've got a couple options. Ours is called Simple Link for all our IoT kind of products. There's, again, a wide variety of different RF capability that we support, things like Wi-Fi, Bluetooth, etc. All these kind of IoT devices, they go into different type of use cases, building automation. We talked about grid infrastructure, medical equipment, factory automation, car stuff. So yeah, lots of things. Okay, so we talked about Jack Kilby. We talked about some of these other ones. Edison, Tesla, of course, kicking off the electric revolution. Transistors, radio communication, these are all super important. What's been super interesting the last couple decades is kind of these major moments. So the PC age, then moving on into the internet. So we figured out how we connect all these computers, building cool stuff with that. Amazon, Google, you name it. Then we went into the mobile age, which was kind of a little subset where we said, okay, we can shrink these computers, have them always connected with the cellular connection, and battery powered, again, some super cool stuff we built with that, Uber, everything like that. And then now we're in the IoT age, which is basically we have all these low power electronics, so they can all be connected to the internet. And then what kind of cool applications can we build from that? We talked about some of those before, but this is basically a mega trend that's happening right now. It's affecting every industry, just like the computer affected everything, just like the internet affected everything, mobile affected everything. Now we're in IoT. That's why all these IoT applications are very interesting and useful. So really exciting time to be an engineer and graduate. I know it's a weird time to be in school, but I promise it's all worth it at the end. Once you guys get out in industry or your final career path, there's a lot of great challenges still to be solved out there. And it really gets exciting when you get your hands on the opportunity to build some of those products and services. So the IoT basically is these three major buckets. So your edge, which is all your connected things, your computers, your phones, etc. They all are generating data or needing data from the cloud. They all need to get that data through the infrastructure, right? So that's kind of the second bucket there, which is your Wi-Fi routers, your cell phone towers, your satellite communication, your fiber optic cable, right? All the stuff that's getting stuff from the edge to the last bucket, which is the cloud. The cloud's your big data centers, right? Your Amazon Web Services, your Google Cloud, your Microsoft Azure, your IBM Watson, whatever it is. And they're all hosting the big applications there. So all three of these buckets have hardware and software aspects of it. And they're all super critical to the overall IoT stack. So even if you're not necessarily building an embedded system or a smart device, you might still be contributing to the IoT, either helping with the infrastructure of connecting the internet or doing the high performance cloud side of things to make all the internet stuff work. Okay, and then another big thing to know as well is you actually have a ton of compute power in your little system, right? So when you integrate a microcontroller or your little microprocessor, that's a very well-spec'd device typically in the modern context. So you could do a ton of stuff just on the device and then send little bits of data out to the cloud. Or you can just have your device stream a whole bunch of data to the cloud, and the cloud, the unlimited compute power of Amazon can compute all that for you. So there's different ways to basically set up how you want to do the data transmission. Like I said, this is why it's all very important to understand how these IoT concepts work. so that when you're doing a system design, you can figure out, oh, okay, well, maybe I want to do a lot of device side stuff, and then maybe a little bit of connected data, or maybe I want to do a whole bunch of connected data on the cloud side. And then from an embedded systems perspective as well, there's different ways you can prototype either the wireless nodes, which are the most common ones. So you have some kind of idea for maybe a smart device or some kind of smart application, connected application. You can basically take like your Launchpad, start building out your sensors or your motor control or whatever you're doing for that particular thing. And then it'll connect up to the internet and do, whatever cloud stuff it needs to do. The other thing you can do is build a gateway. So in some cases, it's not so defined how to get the data from your edge to the cloud. So you may need to build a gateway to help connect those devices, get all their data, through some kind of RF, for example, and then maybe connect that through Wi-Fi or Ethernet or something else to get to the internet. So sometimes you might be building a gateway to help make that connection. And then there's a whole bunch of cloud services, but they could be specific to IoT, because in IoT, remember, we're doing a lot of data collection or something like that, right? We need to store that somewhere, or maybe we need to visualize that on the web somehow, so it's useful. Or maybe there's web developers that want to access some of our data from the IoT devices, or maybe we want to get connected to more of the cloud style stuff. So there's all kinds of different things to help make those connections. All right, and then we're talking about power just briefly. So for many types of things, you probably want to design a battery into the system. This is just for convenience and for a whole bunch of other reasons. There's all kinds of battery technologies you could potentially select. They all have different energy densities, form factors, et cetera. It actually, your power of the system has a major effect on a whole bunch of factors in your design. So this is definitely something, an area you want to spend a good amount of time on. But like I said, here's a few examples like alkaline batteries, lithium, lipo, lead acid, et cetera. Again, it's all design considerations. In some cases, actually, you may need a wired application, right? You need something like an Echo, where it's listening all the time. It needs to be powered. So in that case, we actually want to have a wire to a power supply. But in a lot of times, you do want the battery. Maybe you have to recharge the battery. Maybe it's replaceable batteries. The size of the form factor. Maybe sometimes we're building a very small, thin credit card sized piece of equipment, or maybe we have a bunch of room inside of a big enclosure in like an automobile or something like that. So all those things will have big effects on how your final design comes out. This is a typical block diagram of your kind of IoT system. So you'll have some kind of processor. Again, it could be a low power microcontroller, it could be a microprocessor. You'll have your sensor capability, power we talked about, motor control. Oftentimes we're doing like a lot of automation, some kind of automated kind of project, help make things easier for humans to interact with, et cetera. So we need motors for that. Inputs, outputs, displays, and then whatever our communication is, whether that's wired or wireless. So in the motor control, again, it's all different trade-offs. If you are doing something where you need to move something, there's different types of motors for accuracy of movement, torque capability, complexity of control, efficiency, cost. All these are very important to our overall design. And here's again some trade-offs around the different common motor types, brushless DC, stepper, etc. And then for a display perspective, you might need to get some information out to the user. So you have traditional stuff like LCDs, OLEDs, LEDs, e-paper. These are like low power kind of displays. And then with IoT, you have the option for a cloud-based display as well. So you can do like a web page, or you can do a mobile app, something like that. So again, it's all dependent on what your design is, what kind of information you need to relay. Is it video? Does it something come with a display that needs a backlight? How's it going to mount in the overall enclosure of the final design, stuff like that. So that's displays. And then for wireless, all kinds of choices here as well. Again, you're doing design trade-offs. So some of these you may have heard of, some of these you may not have heard of, but they all have different strengths and weaknesses based on their range capability, bandwidth, how much data they can get through at once, the cost, not just the cost of the module, but maybe the cost of the overall implementation on the network, stuff like that, power usage, and then adoption, how familiar are people with it. So Wi-Fi is really great, really popular in hackathons. It's so ubiquitous, right? We have it at school, we have it at work. Grandma knows how to use Wi-Fi, right? So it's all very nice. We can stream our 4K YouTubes over it. It's got great bandwidth capability. The only downside really to Wi-Fi is just the power consumption, and then in some cases the range. If you're running on a battery, for example, the Wi-Fi devices will roll through that a little bit quicker than some of these other technologies. And then you've got Bluetooth, again, super common in a lot of things because it's all in our phones or tablets, things like that. But it's also kind of a quirky technology as well. Depending on which Bluetooth you're at, we'll use 4 as a common example. 30 to 50 feet of range. Maybe that's good for your application. Maybe it's not. There's the pairing mechanism. There's the stack can get a little bit tricky. So again, trade-offs. You have NFC, more specialized. So RFID applications, smart payments. Again, super dependent on if you need something where you need to be right next to the device to transmit data. And then you have low power wide area networks. This is like Sigfox, LoRa radios. These are all kind of connecting to some kind of central network, some kind of tower or something like that. And oftentimes like a smart city application where you have a lot of devices, a lot of high density of devices, and they need to connect up to something. And then you have cellular, which of course, really nice. It's wide availability, and good bandwidth, et cetera. But then the trade-off being the cost of the implementation. So you have a more expensive cellular modem, which is more than a Wi-Fi or Bluetooth module. You've got a SIM card, you've got a data plan, so that's some of the trade-off there. And then you've got Zigbee, Thread. These are mesh networking type of protocols. So instead of like Wi-Fi, for example, is a star topology, you have a central router or gateway. All the Wi-Fi devices are connecting to that. In Zigbee, for example, you've got node A can talk to node B, can talk to node C, et cetera, and do message passing through the network. So there's certain use cases where that can be really powerful. And then you've got infrared. This is like your TV remote, just a line of sight, super simple technology. And then on the other end of the spectrum, you got satellite communication, which is like anytime you got a clear view of the sky, you can pass data. But of course, the trade-off being it's extremely expensive to use the satellite network. So again, RF, lots of design trade-offs. Typically for hackathon, though, you can usually find Wi-Fi and Bluetooth modules pretty readily. And that's what I probably would recommend. Cloud services, I'd stick to some of the bigger ones. So, Amazon, Microsoft, they do great jobs for IoT integrations and things like that. And those are reliable services. And there's a whole bunch of other services you can find online that could help out with your project potentially. Okay, MQTT, this is a cool protocol just for a lot of IoT devices. So HTTP, of course, is the classic, how we use the internet on our computers, stuff like that. But a lot of these small IoT devices are using this MQTT thing. So that's definitely worth looking into if you're doing any kind of sensor data with the web. There's a lot of support for that and things like that. Your IoT stack is actually pretty heavy. So you've got your actual device, the embedded system, which you have to write firmware for and support, the design for and everything. Then you might have other aspects like your cloud side, like what kind of servers you might be running. You might have an app, mobile app that you have to design, stuff like that. So there's all kinds of little domains of expertise that are required to do a full stack IoT thing. If you can do all that yourself, that's fantastic. You're not dependent on anyone. You can really customize the whole experience. But for a lot of people, that's not an option, right? There's just too many things to work on and get working. So oftentimes people will develop with different services that will help them with certain aspects of their stack. And then obviously you're going to be dependent on those services working for you. Okay, and then let's see. We'll get too deep into this. This one in a hackathon, not as important, but a lot of engineers, I think, make the mistake of just designing for cost, like trying to get the lowest bill of materials possible. But actually, in any kind of design project, the engineering time is one of the biggest factors. And you have to value yourself as an engineer, by the way. Your time is extremely valuable. You don't want to be hitting your head against the wall on badly supported products or anything like that. So sometimes it does make sense to pay a little bit more if it means better quality, better usability, availability of reference designs, vendor support, etc. That can be extremely nice. And of course, that might help you with your time to market or other factors, especially in the hackathon. Time is an extremely limited commodity. So big question we get as well as when is it appropriate to use a processor versus a microcontroller? So microcontroller, being a low power device, think of like Arduinos, the Launchpads, microprocessor being more, high performance, right? Raspberry Pis, Beaglebones, these kind of things. When is it appropriate? So it's a little bit tricky. One is, of course, do you need an operating system? If so, then probably a microprocessor is the way to go. If you don't necessarily need an OS, then microcontroller should be fine. Another big one is cost, and that's a little bit tricky, particularly in a hackathon or where you're just building one of something. You'd be like, oh, well, it's a couple bucks more for the Raspberry Pi, so why don't I just use that? That's true, but when you're building, 1,000 of something, 10,000 of something, 1,000,000 of something, the cost of microcontrollers are significantly lower than the cost of microprocessors. So if you're thinking about a real product stuff, that's why microcontrollers are still extremely popular for many embedded systems. And then programmability, so C programming pretty much is the go-to for launchpads, whereas in a microprocessor like a Raspberry Pi or something, you have Python, you have Java, any kind of language you can think of are available there. So from a software development perspective, if you want to, if you're more comfortable with those languages, there's better software support for your project, then maybe the microprocessor is the right choice, at least for the first go around. But and then lastly is the real-time capability. Microcontroller is much better at real-time stuff. So motor control or anything that's real-time. The microprocessors typically either don't have the dedicated peripherals to do that stuff well, or they have the overhead of the operating system that's preventing them from doing that stuff well in most cases. So less cost, less complicated, lower power. These are some of the big reasons people choose microcontroller. If you need higher performance, if you need more flexibility on the software, then the microprocessor might be a good one to use. Okay, and then I won't bore you guys too much with any of this. We did talk about the Launchpad already. Again, if you have any questions about that, let me know. Your microcontroller, just a few other small differences between microcontroller and microprocessor. So here's a kind of high level about a microcontroller. You've got typically a single core device still for most microcontrollers. So you got one CPU, and then you have the memory inside of the device. So you typically have a mix of RAM and flash memory. For microprocessors, it's usually probably more beefy multi-core. You've got the memory on the outside of the device. Something like a DDR memory or whatever would be external. So those are some of the, again, the big differences between the two. Okay, and then this is the Beaglebone. This is kind of the Raspberry Pi alternate. There's a couple of different flavors of these, but like I said, more beefy processor, more capabilities, more kind of computer style peripherals as well. So you see things like HDMI or USB, stuff like that. And again, power consumption. If you're doing anything battery powered, you do want to steer more toward a microcontroller because the microprocessors are using quite a bit more power. More often than not, and this is not always the case, but more often than not, your processor is going to be the biggest power user in the entire embedded system. The exception being things like motors, stuff like that. Obviously, we use more power, but oftentimes your processor is going to be the most power intensive. So if you're doing battery applications, yeah, microcontroller is probably the best choice. Your microprocessor, you're going to need either a huge battery or have that connected to a dedicated power supply. Okay, we do have a little robotics kit. I don't know if that's interesting to anybody, but we have one. If anyone needs one, let me know. And let me see if I got anything else here for you guys. With the booster packs, these are the plugins, software. If you have any questions on that, let me know. Don't need to go too far into that. Some of you for software on microcontrollers might want to look into real-time operating systems. This is just in general, may not be applicable to the hackathon right now, but for IoT stuff, there are a lot of complexities. So things like the wireless stack, the different things going on, right? You might be spinning motors, you might be getting sensor data. There's just a lot of stuff happening in kind of an IoT system. So a use of a real-time operating system can be nice to manage some of that stuff. So this is, you know, not an operating system like Mac OS or Windows in the sense that it's got, you know, all the features that those operating systems have, but this is kind of a lightweight operating system that can run on your little low power microcontroller, but similarly will help you with different tasks that are happening in the system. So like I said, all those different things that might be going on, you can structure your firmware around that real-time operating system style code. And that can be a big help when your application is being scaled. So just something to consider. There's some stuff like FreeRTOS. We have TRRTOS for the TI stuff. And then also document. I'm sure you guys will have some way to document your project, but I like this particular website. It's pretty cool, called Hackster.io. And this is a project sharing website for electronics specifically. So all kinds of cool stuff. We have a bunch of TI stuff up there, but there's Raspberry stuff, Arduino stuff. If you want to get views on your project after the hackathon, this might be a good place to do it. You can also do, they have Hackaday, they have Instructables, YouTube in general, just all kinds of great places. I just encourage you guys to, if you build anything cool, you know, on your own time, either at these kind of events or in your student clubs or whatever you're doing, be sure to document that. It's cool to share that out to the community, show your parents what you're doing at school, show your friends in other majors what you're doing, or even pull it up in an interview with maybe a future employer. Okay, I think we're running low on time. Like I said, the power area is very important. This is kind of what the last few slides are on. I won't go too much into this because I don't think this is super important for most of you, but definitely keep that in mind when you're doing any kind of design stuff. The power aspect of it is going to be huge. How do you get to the right voltage levels? How are you going to get the different power sources, you know, different types of batteries or whatever hooked into your system? And then how you efficiently feed that. And that's also going to translate into your PCB design, how that's going to get laid out and things like that. So anyway, I'll stop here and then we can do a Q&A if anyone's interested in these topics.
Awesome. Yeah. Well, we already got one. Anonymous is asking, where do I go to understand how to use the TI libraries and how to code a mobile application for my project?
Yes. So to use the TI libraries without being ultra generic and saying ti.com and hopefully dig through and find that yourself. Basically for each processor, you'll have a particular, you know, bunch of collateral. So something like a software development kit or something like that, right? So my recommendation is whatever you choose. So let's do an example. Let's say we choose this sensor tag thing, right? And we want to build a little custom application for this. So this particular development board has a particular device on it, right? So in this case, it's the CC1352R. So there's an associated software development kit with this. There's all kinds of, there's the actual data sheet for the device. There is application notes, white papers, all kinds of stuff. And you probably won't be able to get through that in one weekend, to be honest. But at least that's going to be a good amount of documentation to, you know, fully understand what's happening. And then that's just the embedded side. Then when you're talking about something like a mobile application, that's a whole another domain you have to go into, right? You have to figure out, okay, I'm building an Android app, I'm building a iOS app, blah, blah, blah. I need to download those tools to get started. I need to read those tutorials to understand how to get that whole aspect working. So now you're starting to see the complexity that's required to connect the embedded side to the Internet of Things and then the Internet in general, all the different technologies. So again, time is going to be your most precious commodity. You'll start with the software development kit, hopefully get some example code running with your particular development board. Maybe you can tune that to start working for your application, but maybe not, right? You might hit a wall and may not go as planned. That's just how part of design work. But that's my recommendation. Yeah, pick a development board you think would fit. Get as much as you can from the resources you can get from that, whether that's the software examples, the documentation, and then just try to, work from there.
Awesome. I had one quick one. Do you guys have any like support programs for undergraduate students like looking to pursue designs with TI hardware? I know some places do like small product grants for eligible teams?
Yeah, we do that through the university program, which I'm a part of. So if you have a specific request, just let me know. You can just shoot me an email, I believe. I'll put it in the chat.
Sweet. And then so IoT has a lot of different applications, but what do you think would be a good starter project for someone to get started with this weekend?
A good starter project, I think it's just really whatever you can kind of demo effectively. So to me, with just the very limited time you all have, something where you can get a development board and maybe a breakout board and like wire those together to show some kind of demo would be probably the best starting point, because you don't have a ton of time to really get super deep into anything really. But by the end of it, the competition, of course, is to impress, whoever's judging or whatever. And having a solid demo is going to help do that. So I would just try to streamline, figure out, what's the most efficient way that you can create a demo that doesn't look like a ton of effort, but will be, showcase an impressive application, showcase some complexity, and yeah, that's the best way. So sensors, wireless, those are all good.
Yeah, for sure. I'm taking an IoT class right now, so we've been going over like different Mac protocols and stuff. It's been pretty interesting to learn about. It's kind of like maybe someday when I have a lot of time, we'll get super deep into that. But this weekend, it'll definitely be something quicker like that.
That's right. Yep. Yeah, for most design projects, once you're out in industry, you'd have many months or, even a year, maybe even 2 years to work on something, right? So you can definitely get much deeper, because you're obviously building for quality, building for, all the factors I kind of alluded to in the presentation. Yeah, with just a few days, it's really not enough time to check all your boxes, unfortunately.
Yeah, it's a little tough to get 100 different sensors and spread them across Columbus within just a few days, but we'll see how far we can get. Do we have any other questions from the peanut gallery, from the other panelists?
All right. I don't see any more questions, but I would like to take a second and just thank you, Mark, for a wonderful presentation. That was super helpful. I hope that the rest of our guests thought that it was pretty good too. Thank you for your time and your expertise. Hopefully we'll see you over the weekend during our Makeathon.
All right, very good. Thanks, everyone. Have fun out there.
Have a great night.